We'll start. I'll do a brief introduction. Yeah. Ready for this? And are you recording that too, or? Yeah, let's record now. Okay, all right, great. All right, let's go ahead and get started. Thank you. And this is a total off-cycle sort of seminar. It'll be going all summer long. We have another talk next Tuesday coming up, and then one the following Monday. So just keep that in mind. And what we're doing is interviewing candidates for our geophysics position that was unfilled. We're unable to negotiate with our previous candidates. All three of them accepted positions at other institutes. So recruited away. This is our second go around, and Oscar here is a new candidate. Upon our review, some of you do know Oscar. Hopefully many of you do. Some of you might have had his classes already. He's been part of the department in that regard for several years. He got his PhD from UTEP in 2008, so he's been around here for, wow, it's been that long, 9 years. Wow. And for those that don't know Oscar's background, he has a very different background. He got a 1992 a Naval Geophysical Engineer degree, and I think you're a merchant marine, weren't you? Or? Yes. Yeah. So he did that for a while, and as a student here, he received the Bruce Davidson Award in Geological Sciences, and that goes to the students. It's very helpful to the department and really a major contributor. So it's our pleasure to invite him here today to give a talk. Again, thank you for showing up at this sort of odd hour in a summer day. And Oscar, I'll just leave it up to you.
Thank you. Well, thank you guys. Well, my name is Oscar Dana. Thank you for having me, for giving me the opportunity for having this little presentation with you guys. Well, essentially it's going to be related to how the geology can be applied to engineering scale scenarios, how all the science that we learn here at UTEP can be successfully applied to solve civil engineering or environmental engineering or even hydrological resilience scenarios by using a proper set of geophysical and geological tools. That's more or less the introduction, definition of synergy, science versus engineering, geoscience in engineering, and I'm going to show something on natural hazard, something applied to civil engineering, engineering scale, the differences, conclusions and recommendations. The introduction, well, I'm applying for this position because it's the job position describes that you want somebody that has that can develop projects based on geology but also in engineering. I think that because of my background, I can fit really nice this position. I am an engineer, I'm a geographer and also an hydrographer. I got my master's degree from physics department in applied physics, working with Dr. Doser in really shallow geophysics, and then I did my PhD here in geological sciences. I think that the research that should be conducted on engineering geophysics should be natural disaster resilience, environmental mining assessment and prospection, and also in energy. We are going to focus particularly on this one because it has social implication and the area needs a lot of that. That's how we work, geology, geophysics, geochemistry. We have this kind of a common thing that is called geotechnics, and we can have a significant impact in civil engineering, hydrology, and environmental engineering. That's what we want. For example, this is the blueprint of the Pisa Tower, and they say, let's save some $700 avoiding geophysics and geotechnical work. So they designed it like that, and we know what happened later. Okay? And that's what usually happens when you are developing a project. That's what they really want, that's what you think that they want, and that's what you do. So it's important to know beforehand what your target is requiring. And this is really important, especially with civil engineers, because they want a geological assessment that is helpful for them at the scale that they want the job. We use as a scientist the education to acquire new knowledge, and we seek to know, and they aim to do. That's kind of sort of the difference, but there is a strong link. The science provides the foundation for doing nice engineering. If we don't have science, engineering cannot be carried out because there is not a framework for that. That's for natural disaster resilience. We're going to apply some geophysics for that, and we're going to link it to civil engineering science, hydraulics, and geotechnical. I'm using all of that because they concur on the real scenario when a disaster happens. There is no such a thing that everything is separate. Everything happens at the same time. That's what we have. We are in a vulnerable position, and eventually we want to go to the more resilient scenario. So if we do this, we are going to have some parameters that are going to help us to know how resilient we are, or what's the magnitude of the hazard that we are exposed, and what we know, and what we need to do to fix that. And there is when the civil engineers are required to do some moderate intervention to be more resilient. But that intervention from the civil engineering that have to be supported by geoscience in order to avoid a disaster even worse than we have before they do anything. Okay? Essentially, that's what we have: the conditional factor, the anthropogenic factor, and the trigger factors. Here in the area, I'm just going to show you what's happening in the recent history. We don't need to calculate the statistic of a return period rate. We just can see the press, and we're going to see that we have these scenarios. For example, this is not Acapulco, this is Juarez after heavy rain. Okay, this is Juarez 2, this is Juarez 2. You see the velocity of the flow here, that's pretty bad. And this, well, or we do geoscience to support engineering, or we teach them to swim. That's the only choice that we have in the area. This is the natural condition that we have. Really steep Sierra de Juarez. There is a fault, the Franken fault. The slopes change suddenly, so the velocity flow of the runoff changes from a really steep slope to a really low slope. The change is from 45 degrees to less than 5, so it's foreseeable that we are going to have flooding on the flat plains of the sea. That's the SELT of 2006. You can see this is triggered by the katabatic wind on the Sierra de Juarez. This is the record of rain. Usually we have this average, but you can see that sometimes we have these strong peaks. 500 millimeters, that's a lot for the region, especially if we don't have infrastructure to handle that type of events. This happened in 2006. This is a dam that is completely overtopped. When a dam is overtopped, it's not working. The next step after this is a bridge, and the wall is going to be completely eroded away from the current, and all these people are living just there beneath the dam. This happened in 2006. Actually, the Army of the United States went to Juarez to see what's going on with this dam, because if this fails, the downtown of El Paso is going to be flooded about 1 meter elevation. The water depth is going to be about 1 meter up to the Lagartos Plaza. This is in 2016. You see, people got killed by this rain, and it was only at 23 millimeters in 24 hours. That's not too much, and 2 people lose their life on that particular watershed. It was not an extraordinary rainfall. That's the infrastructure that we have on Juarez. All those things are dams, and the ones in yellow, those are the most compromised. The other ones are more or less not good, but not as bad as this one. So we're going to check some of them in here. We are going to check the integrity of this filtro, and this one, this, and this. These are proposed to be built in order to avoid the volume of water that we get here. And this is a nice render image derived from LiDAR data. We float the plane in order to get data at 25 centimeter cell, so you can get a really nice topographic model of the drainage system of the Anapra watershed. Anapra, that means that if UTEP is right here. If you look here, you're going to see this. This is the hydrology calculations. We can see that the dams are supposed to receive this peak of water and then attenuate the pools from here to there. You see? That's how they should work. Okay? But for example, this one is not working that properly. This is the theoretical scenario for a 500-year return period rain. Let's see how they are. That's why we apply geophysics. This is resistivity. This is seismic, and this is interpretation. This dam is failed. For whatever the reason, it's not an homogeneous structure, and we have these changes between reds and blues. That means that we have some clays in there, and for some reason we have these structures here, which are here. It's clay that it's flowing into the actual dam. This is not a good designed dam located in the Sierra de Juarez. This is Pico del Águila, and our assessment says that it's only worked properly for a 25-year return period. This is the fronteriza. This is the one that was overtopping in 2006. We can see that it was not that bad, except from here. The velocity is not too bad, and this is the velocity, but the profile on the other side of the wall. We can see that we are reaching 600 meters per second. That's not too bad for this structure, but since it was overtopping, it has to be declared not good for containing any water at all. This is really bad. This is clay and clay. They use a clay layer, a plastic clay layer, as a foundation for this wall. And eventually, this structure experienced differential loading, and the structure is completely failed. So, from 4 dams that are supposed to protect that watershed, we have seen that 3 are not working. Those 3 were working in 2006. In 2016, they are not working at all. So that's why we are having that strong flow of water downstream that is killing people over there. Well, once that we check the integrity of the dams, we proceed to do the modeling. This is the Navier-Stokes in 2 dimensions, and these is the results. That's the general result. I'm going to show you, this is one of the dams. This is El Filtro. You see it's reaching 30 meters in depth for a 2-year return period. This is located here. They just put rocks and dirt and everything in there instead of doing this here. This is the rock, this is the Finlay formation, which is a strong formation to place a dam, and instead of putting that dam here, they just put it here. And now it's operating like a dam, but if you are there when this happens, you can hear it's like a submarine in a movie. And it starts to blow water to go, because it's a lot of pressure. 13 meters is a lot of pressure working on the wall. This is another view of the filtro, and that's the system. You see, this is a road that's called Camino Real. It's like Transmountain. And you can see that the culverts are working like retention walls. But the Camino Real is not designed to operate like a dam. It's just a road that is receiving a load of water here, here, and there. So this guy is behaving like a wall, but eventually it's gonna fail. Why is that? Because there are no water contentions upstream. we can see that even for a 2-year return period, we have 1.6 meters of water depth on the lower part of the watershed. That's a lot of water. It's more or less around here. Okay? That's another view of the same system, another view. Here is the Puerto La Paz Dam, which is completely broken, and this is Pico del Águila Dam. Let's check the velocity. It's 4 meters per second. That's 16 kilometers per hour and is per metric ton. So the flow that we have there is 30 cubic meters per second. At this velocity, it's like putting yourself in the middle of the freeway at 5 p.m. Okay? That's what happens if you try to cross this river when this event happens. This is the velocity. Let's check the wave celerity. Let's check how the actual wave is too fast that goes ahead than the actual water. You see? That's the flow number. If everything in green is below 1, everything in yellow or red, it's above 1. That tells us that the flow is turbulent. Okay? You can see that almost the whole river is turbulent, especially here. And you can see how it looks like in this picture that they took on the lower part. You can see how turbulent is that there and there. That's why when this guy tried to cross the river with his car, he was experiencing like being inside of a whirlpool because of the high energy flow that we have on that area. And this is consequence that there are no regulations of the water upstreams because of the lack of geologic knowledge to design the dams on the upstream. You see? This is the person that lost his life over there. This is another watershed in Juarez also. This is 1,000-year return period. You can see that this is an ephemeral laguna. This is known as El Barrial. And you can see this is a huge structure. What happened then is that eventually raining stopped, we have a dry season, and they start to develop a bunch of houses there, but they are inside of the ancient laguna. And now when we have a small rain, all these people is experiencing problems, but not loss of life because the velocity is really low, because it's the time of concentration for the watershed is really low. That's the hydrologic modeling, and that's the result. We propose to develop this 3-meter wall to prevent all this flowing to go into the area which is already urbanized, and they have already worked on that dam. We show them that there is some turbulent flow here. We have some vortices. Let me show you. You see, in this area we have this vortex, so they need to put stones there to prevent that the vortices is going to erode too fast the wall. And that's the elevation that we calculated for that. 1190 for this area and 1187 for the southern part. That's the previous design of the wall, and that's the actual blueprint for constructing the wall. So in my office we do from the hydrology, the hydraulics, the design of the wall, and also the assessment of this. Okay? They built this wall in 2016. As a practice for the guys taking the geophysics class, we conducted a GPR survey recently, and it's already failed. You see? You see this kind of gravel there? The GPR is an excellent tool to look inside of this structure. This is nice, but this, you can see this trench is failed. Why? I think that they didn't have this quality control when they were building, or maybe they didn't calculate the soil parameters to see if they can support the weight of the wall, and they also decided to use it like a road. They allow all type of trucks and cars to circulate on top of this structure, and that's what it happened. This is failed, okay? This is what they propose. Usually they are like Justin Bieber, they are believers, they design believing, they say, well, I think that the permeability is 6 meters per day, and maybe at 11 meters we are gonna find a body of sand to get the water. How do you know that? No, I don't know, I believe, and they design for that. When you do the geophysics, this is not 11 meters, this is at least 70 meters, and then you do the Lefranc test in this red horizon, which is sand because of the resistivity, and it results to be only 3.5 meters per day, half of the time that they have calculated used by believing. So you really need to do the geophysics in order, for example, here this is clay. The water is not going to flow by itself. This clay is going to prevent the water to reach the sun. You need to put your infiltration wells up to here in order to be able to put all your infiltration into somebody capable of handling those volumes, okay? This is the same watershed that we saw at the very beginning. Here, for example, we did some tomography. We interpreted, this is electrical tomography. We were looking for the slope analysis over there. This was done for the risk atlas of Juarez. And with on the tomography, you start to make the calculation of the failure function of the slope. You have the failed entrance and several points where the function can be get out, and you have this thing. For example, here the safety factor is 1.8. It is supposed to be okay. One is in equilibrium, but it shouldn't be. But for these cases, it should be 2.5. But this is in dry conditions. Let's add water for a rain. Then you charge the water for 25-year return period rain. You calculate your infiltration, and then you have your loads. And your safety factor lowers from 1.8 to zero point 0.8. That's unacceptable. This was published in 2010. And in 2014, right there next to the tomography, the slope failed, killing a complete family. This is the press report right there. Even though that they know that that structure was going to fail, they allow people to continue living there. And this is the common scenario for the whole Víboras watershed. That's why we are thinking that eventually maybe in the geoscience without borders, it would be nice to make several profiles across the Víboras arroyo, because people at least they need to know that they are living in a really dangerous area. If the terrain is dry, there is no problem. But if you have rain, everything changes a lot, because you have more weight, and the other thing, your friction function is slower, and you have your failure. This is the value of the calculation. It's going from 1.8 to 0.8 only. This is our civil engineering. We are gonna check. This dam is not built. Here we provide all the assessment, the geological assessment, for designing that wall. That's the hydrology in the area, that's the hydrology network. That's the design conditions. It's gonna be handling 18,000 cubic meters, and for a 10-year, it's going to be almost a million of 500,000 cubic meters of water. That's the result of the electric methods. You can see this is the tomography. We usually start with tomographies of 400 or 800 meters to see more or less, not the regional, but neither the local scale. Then we make smaller tomographies to see the map. Here we are trying to see clays. That's what they don't want. Clays are really bad for foundation, and the clays are mapped here in blue. We tune the color scale to depict the clays like blue. And this is the coverage that we did for the area. This is the students doing the seismic, and they are here on the flanks doing the electrical methods to get information on that. This is the seismic. The seismic is telling us here this red, this is the soil horizon capable of bearing the load for the wall, this one. This is like 3,000 meters per second. So that's a nice horizon for doing that. And also we do the S-wave, and the S-wave is correlated to the standard penetration test that the engineers use like an assessment. So for example here, this is less than 14. This is bad. They should put the foundation up to here. It's about 6 meters in depth. Okay? This is how the seismic is collected on the data. We use this source. The source of this type allows to better peaking of the seismic phases because you have better signal to noise ratio. And that's the preliminary result. You have your penetration test derived from S-wave data, and you can see that you can put, this is the soil level, and you have to go up to 10 meters in order to find a suitable horizon to handle the weight of the wall. This red line is 15 blows on the standard penetration test. So they should go up to there in order to be able to design a proper wall. Here we are proposing them to go up to this horizon here. And this is the preliminary design for the wall. This NAMO name means ordinary water level, and this is extraordinary water level. And you need to have always 1 meter above your extraordinary water for safety, okay? This is the resistivity, and with the resistivity you also get an assessment if you have clays on the area to construct construct the clay court that is required for this type of dams. This is the 3D map of the clay that they have on the area. It's right there at 1 meter in depth. So when they do the excavation to find the foundation horizon, they can take that clay to design the core, the clay core required to avoid filtrations. That's the final design, and these are the moduli. This is BP, compressional wave. This is S-wave. We calculate density, we calculate Poisson and Joule modulus, and those parameters are used by the civil engineer to design the proper wall. The final geotechnical section is this. That's what they use for the final proposal, and this is the slope that they finally decide to do. This is a final blueprint, but this is called a geotechnical zonification. That's for them. They know in terms of the colors where they should go, the depth. That's what they understand. The geotechnical, not the geology by itself, but it's our job to translate the geology into the geotechnical language. And that's the final design for that wall. It's going to be like that. The wall is going to go all the way up to here. Here is the safety spillway, and this is the safety spillway profile. Why there? Because it's where we found the better soil, because this has to be built in concrete, so it has to be put it there. That's why you can put it there. So this is the final design. They take this into the National Water Office of Mexico to get money for doing this. This is like 50 million pesos, more or less, in order to build this dam, which is necessary in Juarez. But this is an example how you're going from the geology up to the final design. This is another survey that we did in the Copper Canyon to design this seed rider. It seems that it worked, I hope for them. And well, here the problem is that it's really complicated to get into the location of the, where they are gonna put the towers to support the cables. So we went walking, and this is one of the sites is here, the other one is there. So we have to go with the taromaras up to here, taking all the seismic equipment to do BP and BS in order to design. There is no way that they can put with a helicopter a drilling machine here. It's really difficult. It's really complicated. And that's the note that we received from the company doing the job. They said that they need rock and soil data there. And the only rock or soil data capable of being taken here is geophysics. Well, the other thing, you can take the drilling machine by pieces and doing there, but it's going to take forever. And that's the result on the north part. You can see the blue part, it's reaching the 6 kilometers per second. That means that that's the healthy rock that you have there. So it's this and it's there. They propose to be here, but the result says that they should put it here. They have to change it from here to there. Okay? And that's what you put in your recommendation and in your conclusions. You say, hey, where you are thinking that this is a safe anchor, it's not. You should move, in this case, 7 meters to the west, and you're going to have a better anchor point. This is the south part. You see? This is the healthy rock, and also here. So they should put it here. Not where it's located, but a little bit to the south. Okay? And this is the flank of the really steep, it's really scarped there. Okay? That was in Copper Canyon, and they use that data. What they do here, since they don't have geotechnical data, instead of going with a safety factor of 1.5, they go for a safety factor of 2.5 because of the data. Now I'm just going to point out the engineering scale. I'm just making a comparison of the Ship Rider project with the Baikal project that I did here when I was student. You see the RMS, it's 2 milliseconds. The depth uncertainty is only 1 meter. So it means that maybe they reach the healthy rock at 3 meters, but maybe at 4. That's the scale for them. And that's the length of the seismic, only 35 meters. One of the students on the launch asked me about that. You have to design your seismic section depending on the terrain. For example, in this case, which is the Ship Rider, you can make longer lines because you are going to fall off the cliff. So it's 35 meters, and that's it. That's what you can do. This is what I did on my thesis. This is the Baikal Lake. I did wide angle refraction survey there, well, the data interpretation, and this is the result. It's showing the velocity structure, the lithospheric velocity structure of the area, and we were trying to map the Mojo to see if the reef was passive or active. Okay, this is the model, and that's the matrix of resolution. If you check the ray coverage, well, it seems that we have a bunch of reflection from the Mojo, but let's see in terms of the RMS. Here on the shallower part is only 76 milliseconds. That's a huge difference from the engineering scale. In the engineering scale, it was only 2 milliseconds. Here is 76, and here is 175. This, when translated into depth, we're talking about 300 meters. That's a lot in engineering, but not here. Who cares if the cross is 300 meters deeper? And in the Mojo, we mapped it at 38 kilometers, and with this error, it will be at 36.67 or 39.33. Essentially, the Mojo is really deep, and it's not reflected any evidence that the asthenosphere is pushing upward. So we might conclude, at least with this evidence, that we don't have lithospheric thinning in the Baikal system. But this resolution is not bad for this study, but it's super bad for an engineering scale. So we have to be aware of that type of differences. Finally, this is another regulation dam in the Sierra de Juarez. We started with this map from Drew Wessendayer. Drew Wessendayer did this map with UTEP students in 1974. That's the regional geology assessment. The dam is supposed to be here. And then you start with that, and this is the transect that they constructed there. It has a bunch of structural details. That's the location of the dam. That's all the work that has been done there. This is really important. You have to measure the joints and fractures to see if there is no communication of the water going around the wall. The first result that we got is that the preferential orientation from the fractures is south, and south is nearly perpendicular to the axis of the water. So in this case, the fractures are not a problem because they are perpendicular to the water flow. So the fracture system is not going to communicate water across the rock from here to there. That's the first point. So it's a location that is suitable to be developed like a wall. This is the area where we are working. That's the detail that we have from this map. This map is a scale 1 to 20,000. It's too much for an engineering project. That's the 1 to 5,000 geology mapping. That's the section that the geologist constructed. And from here, we said, okay, let's do geophysics to check if this model is reflected on the geophysical data. When we do that, we see that the reality is quite different, that there is indeed, well, we're interpreting here a fault, and we're trying to avoid this green because that's a shale formation. Is really weak for bearing foundation for the dam. So we have here the tertiary conglomerates, and that's the electrical tomography. It's 1,000 meters section, and we are penetrating 300, 250 meters in depth. That's still too much for engineering, but it's helpful because you are getting details underground. At least you know that you are not going to put foundation on rock. This is 1/500 scale. You're going from here to there and to there. And you see that the deep that you see on surface is not being reflected on depth. You need to design another type of foundation in this case. This is the quality of the data. This is the zero error. It's almost all the data that you are collecting. And from there, we do the geological section. But for the geological section, we have 4 boreholes here, there, and there. I mean, you still do need to do boreholes with your technical data, but instead of having 24, you order only 4, and the 1 meter is about $100. What you are saving money for doing geophysics. That's the section, that's the tertiary conglomerate, and we propose to put the dam in this area. Let me go. That's the 3D model of the section. And once that is proposed there, you have to calculate with the water load, the safety factor there, how the wet front is going to be migrated from the site exposed to the water up to here. You see, this line has to go down. It cannot be getting outside on the other wall. If this line is emerging here, it means that you have internal erosion, and that's not acceptable for a dam. It's going to fail eventually. So you have to be very careful with this, and we propose to put this clay core and to do this, to put this drain. And essentially, this is the, well, you can translate this into a blueprint for construction. But if you go there and you do the geophysics, you can identify that they didn't put any clay core and they didn't put nothing. They just pile up dirt and that's it. So you can use the geophysics not only for designing but also for supervising what they have done. In summary, that the scale is good to see that there are competent surface exposed geological units, but you cannot do everything just by extrapolating the geology findings. You need to do geophysics to corroborate your geological model. With this, you can see that there is a structural complexity in there, that benigno formation is not following the trend of the deep, and the quaternary fields are less than 50 meters, not 100 meters as is predicted in Drugos and Dyer map. That's understandable. They have been mining all that river sands for construction purposes. And in this scale, you can see details in the quaternary field sequence. You can reveal how the structure is between sands and clays, because they usually take sands or conglomerates for building the protection of the wall. You can see by the electrical resistance tomography that there is no rock foundation available for the dam, that they need to put foundation on sand, and in consequence, the slope ratio should be 1 to 3 and not, well, 2 to, usually it's 2 to 1. That means that the inclination is this, the x-axis is 2 times the elevation. So this is 14 meters. The original proposal was 28 meters for the slope. This revealed that it should be 3 to 1 in order to avoid any leakage there. And you cannot put on the right flank, you cannot put the emergency spillway because, well, it's a surface that can be eroded really easy. It has to be constructed on the actual benigno formation, which is capable of handling the volume of water that you have there. Conclusions, well, know your enemy and avoid disaster. Civil engineers are not our enemies, but we need to learn to understand what they want in order to be able to provide a productive and efficient assessment for them. And you can help them, and also in disaster management of government officers and the National Disaster Office, you can provide a lot of information by integrating the geology, the engineering, and the hydraulics. And the recommendations, well, that's important. Okay? Thank you.
So, what's the percentage of saturation you use when you're calculating the factor of safety?
Excuse me, the what?
The percentage of saturation.
Saturation?
Yes. For the factor of safety, you need saturation percentage, as in how much, water will be in the formation.
Well, essentially, the permeability, you calculate the percentage of saturation in terms of the permeability. That's with the grain size of the material that you are using there. If the grain size is really low, close to clay particles, it means that you have no problem that. And the other thing, you have to check that it has to be compact at 95%. That's revealed by the S-wave data. If the S-wave data is less than 10, it means that you have compactation less than 80%, which is not acceptable for that. The specific value of the saturation, I don't know, but it has to be compacted at 95% to avoid water to find pores and make eventually a channel through the wall. That's what you have to do. So essentially, for example, if we have a wall and we want to see if that is working properly, we can do an S-wave survey there. And if we get that the translation from S-wave to penetration test is less than 10, we can conclude that is not working properly because of lack of compactation on there. Usually they ask for another, for a direct probing, but this is a really good tool for diagnosis of what's going on there. Okay.
So when you evaluate whether or not the dam will work or not work under storm of different magnitudes, have you also looked at the transport of the sediments?
Oh, yes, that's very important because the transport of the sediments usually collapse the drainage network, the sewer lines, and then you don't know. I mean, here, for example, in the Las Víboras Arroyo, the first example that I showed, is really steep. And the velocity, you saw, it's great. So they can transport huge amounts of sediments downwards that when the sewer lines are open, because that's what people do, when they see all this water coming down, they open the sewer lines to handle the rain, and all that sediment, it's put it into the sewer line and it's collapsed. And that's something that we don't understand because, for example, they replace those collectors. They are 1.5 meters in diameter. They are completely unoperational because of the sediment load. It's not going to work at all. And they spend like 700 millions of pesos replacing 500 meters. And putting 3 dams on the Sierra, it's 200 millions. We don't understand why they replace this collector on every 2 years instead of putting 3 regulation dams on the upper part or upstream and avoiding all those problems because the sewer is not going to be collapsed if you have the dams over there because they are going to be also a sediment trap, which is really important. And the other thing, you need to put a channel with concrete walls to allow all the sediment to go directly into the Rio Grande. That's what is required there. So that particular watershed needs 4 new dams and 1 channel to communicate the last part into the Rio Grande to put the water in an efficient way there, and also the last part of sediments that are transported. And it's the amount of sediments there is huge. To calculate that, you have to go there and map the grain size. What we do, we take the samples and we send it to the laboratory to calculate the limits, and you use your limits that you get from the laboratory and you put it into HEC-RAS. And HEC-RAS is gonna tell you with the velocity flow how much mass is going to be transported from the upper part of the watershed to the lower part. But essentially, yes, a lot of sediment is transported.
So how often will you then have to dig out the area behind the dam if this is your sediment trap?
Well, that's, for example, the Víbora, this wall, after this event, if we want to rebuild this one, we need to move all the sediments that were collected in this event. And the wall is like 6 meters, and you can easily have like 3.5 meters of sediments there just because of that event, a 10-year return period. That's why we are proposing to put smaller dams, but upstream, right there on the limestone to reduce the sediment load downstream. But here, in one event, it went from 1 meter to 3.5. It's a lot of sediment with a 10-year return period rain.
That dam didn't have a spillway at all, did it?
They
That actually occurred, they siphoned the water.
they siphon, yes, that's true. It's supposed to have a spillway, an emergency spillway, but a guy put a panaderia there. You know, there is a guy that put to buy bread. He built his business there in the actual spillway, and he is living there. So it's blocking all the water to go on there. So they have to put. That's why I told you that the problem is not only engineering; it's lack of governance. Because somebody saw that guy putting the panaderia. I mean, it's weird to be, and it's actually still there because you can see the spillway, and he put it there, and he has a nice fence and everything, it's dog and everything he has there, and in order to avoid that problem, they have to put those siphons to reduce the load there. What they did with the U.S. Army Corps, they cut a channel From there you can see that there is there is a power plant here. They connected to a channel that they have there, and they were able to reduce the load there. And also the problem here is that they diverted another watershed into this system. You know, this type of decisions that they say, well, it hasn't been raining for 10 years. No problem. They allow people to live in the middle of the arroyo, and they make a wall and diverted the water into here. The extra water, it's 8 cubic meters per second. It's a lot of water. After one day, you are experiencing this. And the capacity of this dam, it's nearly 400,000 cubic meters. It's a huge dam, this one. But this is really dangerous there.
Thank you very much.
Thank you.
Maybe we should sell flood insurance.
Yes, but maybe. Or swimming lessons. Oh.